Okay, we are back here. This is the second part of the video looking at Chapter 7 and some of the problems that we had worked through. The first one we went through 17 and 24. We're now going to look at some other ones here. So 24. The next one we looked at was 29. Sorry, 29, not 27. 29. A little bit of calculus. Whenever you see... sorry if this is not. I'm just going to rewrite this one nicer now that we know what's going on here, because there's a lot of stuff written on here that's not crucial to the starting point. Number 29 here says a force F equals quantity 4xi hat plus 3yj hat, where force is in newtons and x and y are in meters. Acts on the object as the object moves in the x direction from the origin x to x equals 5. Find the work done, where work is the integral of force times the distance there, done by the force on the object. And this is also one where we did the work and then we thought about it conceptually and we're like, oh, that's where we thought, like, why is the answer this? And then it made a lot of sense. So hopefully I can convey that in some similar message here. So we have a force. This is number 29. We have a force here, vector that is 4xi plus 3yj. I also want to point something I mentioned to that student. Notice how I'm writing my I with a loop to the other way. I learned this in college because it's very easy, if you're getting very sloppy, to write an I like that, to write it like this, and suddenly it starts looking like a J. So the same reason that I write my T's like this is so I don't accidentally write it that. So that may be something that you might want to develop to do that. Okay, so that is our force, and we're having to basically take an integral of this. So it says that the work is equal to the integral, and they say here specifically from x equals 0 to x equals 5. So they gave us basically the beginning and end, but we need to realize this is the key kicker here, that's only in the x direction. So here is this, so 4x I plus 3yj, and so we're going to take the integral. Okay, we have one way to kind of express this, if we think about this, is that if we drew this as a block, we say, okay, yes, we have other forces acting out, that's true, but if this represents basically, and using this is 4x, that's the x direction, that's the force of x, and this is Fy, which is 3y here, and then the object is moving in that direction, okay, in the positive x direction. They're trying to figure out, find the work done by the force on the object here. Okay, so we're going to solve this, and then we're going to see, like, oh, how could we have thought maybe more intuitively and not gone through the whole entire problem. So let's go ahead and do the integral. So we would have the work is equal to 4x would be 4 over 2x squared, or 2x squared. I. This would be 3/2 y squared, j. So let's put that. From x equals 0 to x equals 5. Okay, and when we were solving, we were I just same as thing. I was like, oh, we need to plug 5 into both of those, and realized, wait a second here, this is just being plugged into this, so this is 0. There's nothing being plugged, or not even 0. We don't even take that into account, meaning none of the work is done there. And so when we plug in 2x squared, 25 times 2, we get a work of 50 joules. And so we actually solved it one way, and we looked in the back of the book and we're like, wait a second, why is it that? Oh, that makes sense here. If it was saying, well, why was the y direction even given to us? Go back over here. If you remember about Newton's, or not Newton's law, what work equals? It's F cosine theta times d, where this is the theta for this problem. And what they said is that the what force actually does work on here is the one that is parallel to the direction of travel. So F of y does not do any work on this object, just like the force of gravity would not do any work on this object. It's the F of x here. This is why this doesn't matter, because it does no work in the direction we're doing. So this is an intuitive way of saying, oh, we're only looking in the x direction here. This doesn't matter. You could have said, okay, obviously you wouldn't want to show your work, but conceptually why this doesn't matter is that it does no work because it's perpendicular to that. If we plug that in, F equals whatever that theta would be, this is 90 degrees, and cosine of 90 is 0, so that doesn't do any work, where this would be whatever angle would be happening in this direction here, so only the x part of that. Sorry, not 90 degrees. I'm trying to show that that is perpendicular, so it would not do any force. And this is completely parallel, so all of this would contribute to the work. And what is all of that? It is the energy. When we did the integral, it's that amount of energy right there, which went to there, which went to there, which results in the 50 joules right there. Okay, so that's what we came out and realizing there. So we can find the integral, which will give us the integral. Now, had they asked, you said, hey, we're moving in the x direction and we're moving in the y direction, then we want to find the amount of work done in the x direction, the integral there, and then separately we will want to find the work done in the y direction there, and we'd have to approach that a little bit differently. So that's 29. If you don't understand, you can always go back. You can always ask your teacher, or ask me, or whoever. Next one we'll look at, next one on the list, is 33. Okay, 33 is actually pretty straightforward. You get a little excited when you see 33 because it's a black numbered one, so you know it's straightforward. It's not overly complicated. Like 29. 29, you had to kind of like look at the problem, look at the answer in the back. But this is my original work. I'm like, well, what's going on? Why is it that? So 33, and I'll just go ahead and show my work, but I'm trying to show the problem here. 33. If you can see here, I'll go away from that. Hold on. A 0.6 kilogram particle has a speed of 2 meters per second at point A and kinetic energy of 7.5 joules at point B. So the picture here that I drew is we have A and we have B. The particle here has a mass of 0.6 kilograms and 2 meters per second. They ask us at point A to figure out the kinetic energy at point A, and that's pretty straightforward. 1/2 times mass times velocity squared. There is 1.2 joules. Then they ask us here for part B, find its speed at point B. They give us a separate kinetic energy, which is 7.5 joules. So we use the same equation, knowing the kinetic energy and the mass, solve for V, and we get 5 meters per second there. There you go, straightforward. Then part C, they say, what is the net work done on the particle by the external forces? And this is where understanding the work kinetic energy theorem is here. This is the work kinetic energy theorem. This is the equation. We don't necessarily need it here. All we need to do to find the net work, I guess the summation of that, is it is the change in kinetic energy, as I mentioned down here. So how much kinetic energy we have at B? At 7.5. How much do we have in the beginning? 1.2. Subtract the 2, 6.3 joules. That's the net work. So that one is knowing how, that mass, velocity. But it's understanding when mass and velocity are mentioned in this chapter, kinetic energy is coming in. When force is mentioned and distance is mentioned, you're mentioning about work. So, so we'll look at another one that builds on that there. So that is 33. As you can slow that down, replay it there. That's why I'm going a little bit quicker here. The next one we have is 34, which is on some other paper. Okay, 34 is also pretty straightforward. How do I know? Because it's a black numbered one. 34. A 4 kilogram particle is subject to a net force that varies with position, as shown in figure P7 1.5. To show you what that is right quick, this is P71.5. So what we'll need to do, basically, let's go back to what they're asking here. They said the particle starts from rest at x equals 0. What is its speed at x equals 5, x equals 10, x equals 15? Okay, so they're talking about the figure, and if we go back to what the figure is here, it's relating force and distance. Force and distance. I feel like I talked about that. That's work. They're saying real loud that you have work. But they're also asking you to find the velocity at certain points of that. So that is the work kinetic energy theorem. Sorry, I'll show you. And you say, well, why don't you have a delta in front of it? I guess technically I have a delta in front of it here, but remember, it starts out at 0, so the kinetic energy at x equals 0 is 0 here, is equals 0. So we don't need to take something minus something. We're just finding it at those points. So comparing what it is minus 0 is that original one. So this is this equation right here, rearranged. I have the 2 over here. So f of d times 2 divided by m square root. So we in figure, if we look at the figure here, at 5 meters, it's 3 newtons of force. At 10 meters, it's 3 newtons of force. And at 15 newtons, it's 0 meters. So I've written that out here at the 3 different watts. And I basically we just solve for v for each of them. So 3 times 5 times 2 divided by 4 is that velocity. That's what it is when it's gotten there. 3 times 10 times 2 divided by 4, that's 3.87. And then the last one, there's no force being applied. So if there's no force being applied, the biggest thing about work, doesn't matter if that will equal 0. So if there's no force being applied, you can't increase something's kinetic energy. You can't make it go faster in this specific case. So it has a velocity of 0. So understanding, like, how do I know it's work? How do I know this? Force, distance, got to be work. When they mention velocity, there's this connection. That is key, because it may not be an equation written anywhere, but if you understand that, this will be written somewhere, this will be written somewhere, but probably not this relationship. So that's why that theorem is so powerful, because it helps you eliminate a lot of mess. Okay, so that is 34. One more, 37. We're almost there, and it is the longest one. As I said to the student who had to leave and was thinking about, should we do this one because it's really long? I was like, well, do we want to end on a layup like 34, or do we want to end on a full court shot at the last second buzzer beater to go in, which is 37? And 37 is not that bad. Actually, 37 is something I actually want to probably do maybe someday in pre-AP physics as a review. So one of the things about this review here, when you see these review problems, it's secretly making you do stuff all over again. Okay, when it says review, what is it going to have in there? Likely linear motion. Okay, the 4 equations. It's likely going to have, maybe not projectile motion, but sometimes they do. It's going to have something about work, kinetic energy. It's going to have something about forces. So you're having to do that so that you're not having to cram for it at the end. The idea is that you go longer and longer and longer, and you keep doing the stuff over and over and over, and then you start getting to points like, oh, that's easy. It's only linear acceleration. Whereas earlier in the year, you may have been like, oh, linear acceleration, I don't know what's going on. That's the point. We teachers, we are secretly tricking you to help you. Okay. So this one's pretty kind of messy here. There's some things I wrote on here that don't necessarily have to do with the conversation that we were actually having. Cross those out real quick. That was a discussion about the third law, where it was derived from. Okay, so let's go over 37. This basically is saying you can think of the work kinetic energy theorem as a second theory of motion. Okay, more force makes it go faster. F equals ma as well. Parallel to Newton's laws in describing outside influences, so a net force causes an acceleration. Affect the motion of an object. In this problem, solve parts A, B, and C separate from D and E, so you can compare the predictions of the two theories. The first one says a 15-gram bolt is accelerated from rest to a speed of 780 meters per second inside a rifle barrel of 72 centimeters. So I have that written right here. It goes from 0 to 780 in 0.72 meters. Part A, it says find the kinetic energy of the bullet as it leaves the barrel. So there's air resistance. At that point when it leaves the barrel, it's going 780. So kinetic energy is 1/2 mv squared. 1/2 times the mass, 15 grams or 0.015 kilograms, times 780 squared, you get 4,563 joules. Okay. Part B, use the work kinetic energy theorem to find the net work that is done on the bullet. So the work kinetic energy theorem is this. Now, it should be just the same. All the work that was done in speeding this bullet up. There were no other influences on it. It was only that. So you could just say 4,563 joules. We can say it's that minus 0 because it's delta, because at the beginning it wasn't moving. If it was somehow moving in the beginning, then you have to subtract it, like the last one we had where you had it going from A to B. But that the work done to speed it up to a kinetic energy, remember I said work is how you put energy into a system. All the work that was done to get it to this kinetic energy and that speed. So that's the answer for B, the net work. Part C says use your result to part B to find the magnitude of the average net force. Average net force is just the net force this case, because the force it's obviously changing as the gases expand. So we use the work kinetic energy theorem. Work is also force times distance. The change in kinetic energy we just found. And the distance of the barrel is 0.72 meters. So we know this, we don't know. We're trying to find the force. We know the distance, we know the change in kinetic energy, and we can solve for the force. So 4,563 divided by 0.72 is 6,337.5 newtons. This is very important because that's what you're going to compare it to. So that was doing it all with energy. Okay. This might have been hinted at by your teacher that there are multiple ways of solving this, and sometimes it's easier to solve it using energy, while sometimes it's easier using acceleration. Okay. Part D, so this part is separate, says now model the bullet as a particle under constant acceleration. Constant acceleration, we have those nice linear acceleration problems or equations. Find the constant acceleration of a bullet that starts from rest, VI or V naught is 0, and gains a speed of 780 meters per second, so that's VF, over a distance of 72 centimeters, or your delta x, or your displacement, is 0.72 meters. A good old equation here. We have final velocity, initial velocity, we have displacement, and we don't know acceleration. So in my class, we always called this the fourth equation. We have the final velocity, initial. We plug all that in and we get 4.23 times 10 to the fifth meters per second squared. That makes sense. One of the things I was saying to the student is that's why bullets are made out of metal. There was a Mythbusters. As the meme goes, there's always a Mythbusters for everything, where they tried to see if they could fire an ice bullet. Because if you assassinate someone with an ice bullet, they can't find the bullet because it melted inside the body. But it never worked, even though they super froze things, because the acceleration of this thing along, even though they protected it, from the fire of the explosion, the acceleration was so great that it just basically broke apart in a million pieces. So that's why it has to be at a strong metal. Now, this is the number, but this is in scientific notation, which is usually appropriate, but I want to make sure we use this number because we're trying to compare it, and this is a rounded number while this is the actual number that we have here. So just for showing and comparing these. Part E says, modeling the bullet as a particle under a net force, find the net force that acted on it during its acceleration. And this is when we both said, hey, that's an easy problem. The net force here, or the sum of the forces, is equal to mass times the acceleration. There are no other forces that are acting on this in the direction that is accelerating it. Force of gravity is not acting in the same direction. There is no drag force, thankfully. So we have the mass, we have our acceleration, and I used the actual number because if you use the actual number without rounding, you get 6,337.5 newtons, which, is exactly the same as this. If you use the rounded scientific notation, it's like 6,345, but to show, to really hit it, that those two are the same. And this is really pretty cool, because there are some times that you will see in your AP problems, AP tests, where there are multiple ways you can solve it. It may be faster to solve it using linear motion and friction or one direction. You may think intuitively like, oh wait, I don't have to solve it the same way. We'll see later that you can actually solve projectile motion problems using kinetic energy and potential energy and back and forth. So that was really, and then F is just what do you notice? And we're saying 2 different ways to solve it. So that was a pretty interesting one, and the review. So that ends up the problems that we went on here. So I hope you appreciate it. Wow, 20 minutes again. So okay, I'm going to go ahead and sign off. Hope you like it. I'll get these loaded as soon as I can. So have a good weekend.